All right, let's go ahead and get started. Are there any questions before we begin? And of course, don't forget, right, the extra credit opportunity that we mentioned on Mondays. We mentioned you could do some activity, apply for scholarships, or apply for an internships, and all of those would be worth 5 points per activity. So if you have questions, you can always ask me about it. All right, let's go ahead and talk about chemical equilibrium then. And so this is related to your lab this week. So we have time, we might talk about your lab, since I think everyone's done it now. And so let's look at this example. And so let's think about hemoglobin. And so we have hemoglobin here, so it's this protein, and of course it has iron in these active center here. And the important part that we care about is that it binds with oxygen. And so now we kind of have to think about this equilibrium process and how that works to bring oxygen to our body. And we have this equation too of non-complex hemoglobin plus oxygen, of course, makes our complex hemoglobin oxygen molecule. So then if we think about this, so let's start in the lungs, right? And so in the lungs, we have a high concentration of oxygen, relatively speaking. And then if we have, right, our hemoglobin not bound to anything, so it probably just came from the muscles and is lacking oxygen, so they combine, right, in our lungs to make our hemoglobin oxygen. And so then this hemoglobin oxygen complex molecule floats around, maybe goes to your leg or something. And so then in your leg, right, the concentration of oxygen then is probably low because your leg has moved and consumed that oxygen. And so in that environment, then if there are no reactants, right, then it's going to cause our reaction to shift back towards the reactants, so towards the left. And so that causes, right, the hemoglobin then to release the oxygen in your leg or whatever other bodily extremity. And then, of course, then the naked hemoglobin comes back and makes its way back to the lungs to start that whole cycle over again. And so that's how equilibrium is used. And so we could also think about, I didn't mention it in here, but if you were to look into it, so there's also, what's kind of interesting is, so there's a thing called fetal hemoglobin. And so that's also what drives the difference and what makes it so the baby can get oxygen. And what's kind of fascinating and why it's called fetal hemoglobin is because it actually has a different binding constant. So that's how, right, the mom is able to then give oxygen to the baby, and then with this fetal hemoglobin, it has a different binding constant so that the baby can get oxygen as well as the mom. So all part of dynamic equilibrium. And so now let's talk about some of these arrows. And so normally we've just seen this kind of single arrow. So that implies, right, it's just one product, usually going to completion. And sometimes we've kind of maybe seen this like no reaction. You could put NR, oh my gosh, can't write today. NR or no reaction. So we've seen that, in lab with like the copper and the acid. But now we're introducing this new arrow. So now we have this equilibrium arrow. And so let's just put it a little aside. And so this is not to be confused with resonance. So what's resonance? So let's remind ourselves what resonance is. What does that mean? So resonance is when we kind of just move the electrons around and we don't really change anything. And so the quick example that I can give that I think we've seen is we talked about this molecule benzene and how you like to draw it like this, indicating our double bonds. And we can draw a hydrogen, so every carbon has 4 bonds. But then, right, we said that this structure really means that these double bonds are delocalized all around this ring, aka we could draw it where the double bonds are in a different position. And so we can move the double bonds around. And so all we're showing is electron movement here. All right, so that's resonance, right? So that's compared to equilibrium. So resonance, you might want to add to that just like electron movement. So not to be confused, and that's where it has that double-headed arrow. So when you're just showing electrons moving around. But our equilibrium, so this little double-headed half arrow, so this shows that it's in equilibrium, which is really saying that our reaction can go forward and backwards. So again, right when we see that equilibrium arrow, so it may shift right forward, may shift back towards the reactants, depending on the conditions. And so that's what you saw in lab. If you think back right to the little test tube, the little dark red test tube with the iron nitrate and the potassium thiocyanate, how you mix that, right? You stressed it out, then it got lighter or darker depending on what you did. And so that's just showing that that reaction, that system is in equilibrium. And so then we won't do too much math with this. This is just kind of showing you where the equilibrium constant comes from. And so you do want to be able to at least translate this sort of expression to an equilibrium expression. So let's just see what this is. And so our equilibrium, it's basically trying to tell us which way does a reaction favor. And so, right, we can just kind of generally think about K as products over reactants, right? It's just basically a ratio. And so notice it is actually unitless. And so let's see what it is. And so, right, if we just have this general generic equation of, and notice, right, they have the coefficients. So these, of course, would balance out the equation. And so it comes out to, again, products on top, reactants on bottom. So reactant C to the power of C, so whatever coefficient you use to balance it. And so this is also concentrations. And so usually if we were in solution, this would be molarity. And then we won't go into it, but gas is kind of related, but slightly different. But you could plug in gas values as well, but it's just the gas and the molarity are not equivalent. So I'll just put could use gases, which would be a pressure. But we'll mainly focus on molarity. And then notice, right, then you multiply it by your other reactant to the power of your coefficient, and then all over your total reactants, so whatever your whole reactants are, again, to their power, times your second reactant to its appropriate power. So not too bad, we just have to be able to follow that form. And so again, those lowercase letters represent your coefficients. So as long as you have your balanced equation, it should be relatively straightforward to translate this into our equilibrium expression. All right, so now take a look at this reaction. So see if you can write the equilibrium expression. try to show the notes. Can you see the problem? Do we have an expression written down? I'll give people another minute or so, it looks like. So let's hear what you got. So products over reactants, so of course product side, reactant side. So then what does that look like? Jack, what did you get? Yep. And then yep. And then all over. Yep. So is that what everybody got? And so that's also what is shown here for the answers. So again, not too bad how to do this. And again, don't forget, right, these brackets just signify molarity. And if I were to make you calculate it, I would just give you the values, at equilibrium. Here's the concentration of NO2, O2, and N2O5. What's the value there? So that looks good. And then, so let's look at, so what does this K kind of tell us at least? And so we have our kind of three main scenarios. So of course, what happens if our K is greater than 1? And again, we'll just kind of think about it oversimplified because it's products over reactants. And so if we're saying, right, K is greater than 1, then we're saying that it's favoring the products, right? So it's mainly going to the right. So in this case, if we're looking at this reaction, so we have hydrogen plus bromine gives us hydrobromic acid. And of course, they set up the equilibrium expression just how you would expect. And then they tell us that the K value and is 1.9 times 10 to the 19th. So pretty large. I mean, that's like outrageously large. But all that's really telling us is this reaction really favors the equilibrium to the right. So you're going to have a lot of HBr product in there and not a lot of hydrogen or bromine. Oh, it just means much greater than. Yeah. And that's why they kind of pick the ridiculous number of 10 to the 19th to show you like, oh yeah, it's really, extreme to the product side. And so then the converse, so now much less. And again, we'll just set up simply, okay, products over reactants. And so now we're looking at this reaction of nitrogen plus oxygen makes NO. And so it says that in this case, the value of K is 4.1 times 10 to the negative 31. I mean, that's crazy tiny. But of course, if we think about this, that kind of makes sense. So our atmosphere is a lot of nitrogen and oxygen, so we wouldn't have anything to breathe, right, if this reaction was highly favored. So that makes sense why it's such a low equilibrium constant. And again, all we're saying is there's mainly a bunch of nitrogen and oxygen, and we know from our experience that yes, that does make sense. And so again, we get an extremely small number showing that our reactant side is favored. And then of course, right, kind of the last scenario, which we didn't put on here, but of course if K then is about equal to 1, then of course, right, again, products over reactants, then, right, they're about the same. So any questions on kind of this so far? All right, so now let's look at Le Chatelet's principle and what this means. And so Le Chatelet's principle is really just a fancy way of saying how can we predict which side of the reaction the whatever our perturbation will do. So kind of like what you did in lab, right? You took your solution, and so now how can we predict, so obviously you saw the results in lab, but how can we just predict what might happen without running the experiment? And so now, this gets kind of wordy, but let's just break down what it's trying to say. So it says once a reaction is at equilibrium, the concentrations of all the reactants and the products remain the same. And so that doesn't mean that there's no reactions happening. So on like the individual atom scale, right, there's still a lot of change going on. So that poor one atom, right, could be reacting, and then the other ones, right, going back and forth. But overall, right, the concentrations would be the same. So there's still reactions going forwards and backwards, but no overall change in concentration. And then, of course, if the conditions are changed, though, then the concentrations of all the chemicals will change until you reach your new equilibrium. But just keep in mind, so K is constant. So whatever your equilibrium constant is at a certain temperature, that constant will not change. So I'll just put at same T. But again, in this class, we won't really go too much into the math, so you won't have to do like the math of that. We're just kind of thinking K is always constant, so you have that kind of framework. And so again, we'll kind of talk about what this means with the new concentrations. This will make more sense when we look at it visually. But again, the key point is the equilibrium constant will be the same. And so again, right, we're just going to learn how can we predict the effects of changing our conditions to predict the equilibrium. And of course, right, if we disturb the equilibrium, then that means that not only will our reaction shift to minimize the disturbance, but of course, if we disturb it, that means we're opening up the system, right, and messing with it. Again, just thinking back to lab, that's why you had your test tube that was your constant test tube, right, your comparison, and then all the others, they were essentially open, right, because you're adding something to them, you're disturbing their initial conditions. All right, so we're going to see, so what happens if we add reactants? So we'll go back to the words, but let's find some graphic representation here. And so now we're looking at this reaction, and so it's just either the decomposition or dimerization of NO2. So we have dinitrogen tetraoxide, and then it decomposes to nitrogen dioxide. And so it says, well, what happens if we add reactants? And so that's done on this side over here on our right side, at least how it's formally set up. So if they said that our dimer was a reactant, and so now look at our graph. So first, of course, we were at equilibrium. Again, this doesn't mean that these aren't changing back and forth. It just means that the overall concentration is the same. And then we opened up the system right here and perturbed it. And so we artificially added a bunch of reactant. And so, of course, notice what happens. So we can kind of see graphically what's happening. It's like, okay, first we have a large amount, but then it's decreasing until we establish our new equilibrium. And then if we added a bunch of reactants and it decreased, well then that means that it favored the product. So we added a bunch of reactions, then that shifts it to the right, and then we see that in this graph here with our now growing concentration of NO2. And then again, now equilibrium gets reestablished. So not the same concentrations as before. So that's kind of what it mentioned, right, is that you have new equilibrium concentrations. So yes, they're different values, but our K is still the same. And so now let's go back to all the words and make sure that we understand it all. And so let's look at, so then it makes this statement that says, as long as the added reactant is included in the equilibrium constant expression. And so that means for us, it usually has to be like an aqueous thing in solution. So that's what we're generally looking for. And then it makes a statement, as long as it is not a solid or liquid. So what it's saying is, like, let's say, you were reacting a pile of carbon, with some oxygen. That's a really bad pile of carbon. But basically, if you have a bunch of solid carbon, right, adding more carbon isn't going to increase your concentration of a blob of carbon here. So it's just a solid blob of carbon, right? It still just has to react at the surface. So that wouldn't change anything with the equilibrium. And so same thing with a liquid. And so we don't see too much of this in our class, but sometimes you have a reaction and they're called neat reactions. And neat usually just means that they're not done in solvent, but rather that the reactants themselves are the solvent. So maybe you have a liquid reagent, could be some organic solvent, some alcohol, just anything that's a liquid. So I'll put AKA, your reagent is a liquid. Right? And if your reagent is just a liquid, again, that's not going to change the concentration if you add more pure liquid to it. So it doesn't change the concentration, so that would not affect the equilibrium expression. So again, we probably won't see that in this class, but you should at least be kind of aware of that. All right, so now we deciphered that. And so, okay, going back to this. So how does adding a reactant affect the forward rate? And so, right, this is a very wordy way of just saying what we saw visually. So it initially increases the rate of the forward reaction, and so we see that, right? So it's ramping up production of the NO2. No initial effect on the reverse reaction rate. And then we saw that with the reaction proceeding to the right, so favoring your products, until we restored our equilibrium. And then so it mentions our reverse reaction. So again, our reverse reaction is not affected. But then of course, and then this is extremely wordy, right? It says you will have more products than before and less of the non-added reactants than before and less of the added reactants. And so in this case, we didn't have any non-added reactants. So this was, again, that was just a really wordy way of saying, let's say we had some oxygen involved in this expression. So obviously if we had another reagent, that would be decreased because it was going to our product side, but that wasn't the case. And again, it mentioned that we'll have more products and less of the added reactant. And again, all that was saying is we artificially added a bunch, but then we consumed some of it as it was pushed to the product side. And then it mentioned something, right, you have more of your product. And so again, right, that's all that's saying here is that we make more of our NO2 as our equilibrium pushed it to the right. So pretty wordy, but it's really not saying that much. And so again, how will it affect K? It doesn't, right? So again, our equilibrium constant is the same. And so now let's take a look with removing reactants. And so again, let's look at our graph before we try to decipher all these words. And so looking at this kind of graphical representation, and so actually they didn't show the removing the products graphically. But if we look at here, so they're adding the products instead. So again, they artificially added them. And so once again, right, it's pushed to the left side, creating more N2O4. So we see that again. And then again, new equilibrium is established. And so now going back to this case, so now let's think about this visually. And so again, thinking about our reaction, let's think, so our dimerization, so N2O4, making NO2. So now it's saying if we remove our reactants, so you can imagine, if we remove our reactants, it's going to drive it back to favor, right, making more reactants. And so we can see that, and once again, right, it brings that same caveat, as long as it's not a solid or a liquid. Okay, check. Again, should be aqueous or partial pressures of gases. And so how does this affect the forward rate? And remember, we took away reactants. So initially, if we remove reactants, we would see a decrease of the forward reaction. That kind of makes sense. But then your reverse reaction is still at that same rate. So hence why it makes our reactant. And so this means, right, it's going faster in reverse, and then, right, it proceeds until equilibrium is restored again. And then, of course, right, all this wordy thing to say that, of course, right, we would have less product, obviously, because that product made reactant. And then if we removed our reactant, right, we would have more than we had than when we removed it, but of course not all the way much as our original amount. And of course, once again, the key is that K remains constant. blah, blah, blah. And so again, this is just reiterating the same thing. So if we add a reactant, then it decreases the amount of other reactants as it consumes those and obviously goes towards the products. If you remove a product, that can also be a way to increase products. And so this is actually a good way to drive a reaction forward. And so this is now a practical application, at least, of this process. And so one example, oh, why did this link out? There we go. And so one example of this would be in this Dean-Stark apparatus. And so basically this Dean-Stark thing is used anytime that you're trying to drive off water. And it could be several different reasons. So maybe your reaction produces water, and if you want to keep it going, then you want to, of course, remove the water, or maybe you're actually trying to remove water itself. So we, in class, right, we did the magnesium sulfate, but for instance, this compound here, so nickel chloride hexahydrate, so you can convert it to the anhydrous form if you take this Dean-Stark apparatus and then you boil it with a bunch of toluene. That'll actually drive off the water here. And so right now, Le Chatelet's principle comes into play. So whatever your reaction is, you can have it here boiling. And so then it's going to boil and go up here. And then your solvent's going to collect in the Dean-Stark. And of course, you want to plan it properly. So most organic solvents are less dense than water. So that's how it works. You can't use an organic solvent that's more dense. And so the idea is your water with the greater density would then fill up here on the bottom. Your organic solvent, if it ends up all the way here, it can flow back in. But then you can, right, physically remove that water. So that's why it has a little drain stopcock there. So then you open it up, drain out your water. So now you've removed the products, you've removed your water product, and then that continues to drive your reaction forward to completion, or if you're, like I said, purifying this nickel chloride, then that gives you nice yellow anhydrous nickel chloride. That's one way to use Le Chatelet's principle. So let's look at your lab now. Sorry, give me a second to pull up. And so now let's see if you determined whether your reaction was endothermic and exothermic, and why. And so kind of part of this Le Chatelet's principle is that we can kind of treat heat as either a product or a reactant, right? So if it's an endothermic reaction, we said that, right, it needs energy. And so then we can have heat. So this is, the little triangle is sometimes the symbol for heat in chemistry. So we can have heat then is a reactant. At least that's how we can think about it. And if it's exothermic, right, energy is released, and we said that's in the form of heat. And so that means that our heat then is a product. So now let's look at our lab reaction. And so we set up this scenario, right? So we had iron 3 plus our thiocyanate, equilibrium arrows, Fe, CN2 plus, so complex. And of course, the other key was that your reactants were more lighter or yellowish. And then the product, right, was of course that stark blood red. So now just based off of Le Chatelier's principles, and you can tell me whether your lab results matched. So what happened, or what would we expect to happen when we add our iron nitrate? So we're adding reactants. So which way is that going to shift it? What do we expect from lecture? What do we see in lab? So what do we think? You can look at your results, but what do we predict by Le Chatelier's principle? To the left, or? It became lighter when you added iron? So what did we get? Or what do we expect? So it should get darker. So is that what people observed? I see some nods. And right, that's what we expect. So we can go back to Le Chatelier's principle. We said, well, okay, we had our test tube, right? It starts off at equilibrium. And then if we add more reactants, that should drive it towards the product side, so it's darker. You can also put shift right, so, or towards products, so any of those would be appropriate. And so what about the next thing? So it told you to add more thiocyanate to it. So what happened? What do we expect to happen from Le Chatelier's principle? So what do we predict just based upon this reaction? So if it's at equilibrium and you add reactants, which way does that shift if you add reactants? To the right. And so hopefully you saw that. It should have been darker. Exactly. So we expect it to shift to the right. It's going to make more products, or towards our products. So that's good. And so then we went to the next kind of scenario. And so it told you to add hydrochloric acid. And so it did make a note in there to try to help you. So it says that it removes iron 3 plus ions. And so if it's effectively removing our iron 3 plus, which way is our reaction shifting towards? To the left, exactly. And so, right, if we remove our products, so just like it had said in our big word, well, now it's going to want to make more to compensate. And so, yes, we would see more. And of course, we would have increasing concentrations of just our potassium thiocyanate. So, excellent. So, shift left. So, towards reactants. And then I assume everyone saw that this got lighter then, which matches with our theory. And then, so what about the last bit? In the last bit, is usually the trickiest one. But it said something of place your test tube in hot water. And so we have to think about this for a second, because we don't really know what it's supposed to do, right? We kind of are lacking some information. So what do you notice when you put the test tube in hot water? And what does that tell us? So it got lighter. So what happens, what does it mean then if it got lighter? So then it went to the left, and let's rewrite this for a second so we can think about this. So iron 3 plus our thiocyanate made our complex. So if it's getting lighter, it's moving away from our product side. What can we tell about this reaction? Is it endothermic or exothermic? And it's shifting backwards. Exothermic, exactly. So it's exothermic, right? So that means heat is a product. So now this kind of helps us. So, okay, let's go with that statement. So if this reaction is exothermic, that means heat is our product. So then when we put it in heat, it goes away from that. So, right, it doesn't want to make any more heat. It's already releasing heat. So it's going to shift away, going back towards the reactants, which is what you observed. Excellent. So now we know it's exothermic. And so that was the key point of that. And of course, right, if the reaction had been endothermic, then it would have been, dark red as it was driven forward. And so that's a good way to test whether something's endothermic or exothermic. All right, we still have a few minutes before I'll give you a quiz. Let's just do a little practice on what the worst the math could look like for your exam. And so let's start with this because we've already looked at it and we wrote it out. And so we could have a question then that says, so given the above expression, calculate the equilibrium constant. Given that your N2O5 concentration is 0.313 molarity, your O2 concentration is 0.162 molarity, and that your NO2 concentration is 0.227 molarity. So take a few minutes, plug that in. Yeah, 227. I don't know if that helps if I cross the 7. So what do we get for our answer? So when I shout it out, I can plug it in. So it should have been 0.227 to the power of 4, and make sure you guys help me out on this math, that I don't plug anything in wrong, times 0.162 divided by 0.313 squared. So did we get this value? All right, excellent. I see some nods. The other people get this. So again, not going to be too difficult. So just can you, right, take values, plug it in, write expressions. That's going to be the worst it's going to get. So then we can say our K is 0.00439. And again, unitless there. And so if you want to have more fun with equilibrium, I would encourage you to take the Chem 200 level series. So there, we take a much deeper dive and do fun algebraic expressions and solving stuff. So that has a lot more math involved. All right, I think that's mainly all I wanted to mention. Although, maybe in these last minute of time, I'll mention a reaction that's a good example of one of those solids. And so this is kind of an interesting scenario. So if you have this reaction, so calcium carbonate, and notice the S for solid, equilibrium arrows, calcium oxide, solid, plus CO2. And so the only thing that you can influence to change this decomposition is to remove your CO2, right? So if you remove your CO2, that'll keep driving the reaction forward. But this would be a case, right, where it doesn't matter. You could add a new pile of calcium carbonate, but it's a solid, so that doesn't affect the reaction rate. Same thing with the product of calcium oxide. You could dump a bunch of solid calcium oxide, does not influence the rate. So I at least wanted to show that so you would have some example of where equilibrium doesn't matter. All right, that's probably a good place to stop. So give you your 10-minute break, and then of course ask questions after your quiz if you have questions or need help, and then I'll try to pass back some of the labs that I've graded for y'all.